Today we will cover 4 topics. And the first 2 topics, I already give you some introduction on the first 2 topics. And the last 2 topics will be new stuff for you. And this PDPSD stands for positive definite and positive semi-definite matrix. Negative semi-definite. And that's the definition for linear functions, for defined linear functions. Okay. So today I will give you the brief introduction on the linear functions, which is a very popular tools for analyze nonlinear systems. You can also use linear function series to analyze linear systems for sure. Okay. So for a solution to be exist, we have mentioned that from previous time, that given an ODE, how we can evaluate the solution, the existence of a solution, right? So given this nonlinear ODE, okay, with some initial conditions, we can evaluate that fx. We can evaluate this behavior, these solutions, based on the fx. So if fx is continuous in some local area, local region R, right? Then if it's continuous in this region, then given which contains the initial conditions, then there will exist a solution for this dynamics with initial condition at S0, right? That's existence. And any question here? This will be the last chance that we talk about this, okay? So an example of this, which have no solutions, if you start at 0, okay? Because this fx, which is the square root of x, is not defined at 0. This is initial condition at 0, okay? It's not defined, so which implies this fx is not continuous. For uniqueness, there's one more condition, which is the partial of capital F have also be continuous, right? Which implies fx is Lipschitz in the same area R. Then if you have any initial conditions x0 in R, then it guarantees you have a solution in this local area R, okay? And this is another example which says if you start at 0, you have multiple solutions, which is solution 1 and 2. Okay, both are the solution to these ODEs because fx is not Lipschitz. Okay, it should especially at 0. Okay, so okay, any questions? No. Okay, so next is you might heard this before, slightly more control, but maybe it's fine that you don't know what is slightly more control. But if you heard about this, it's great. So there's a problem in this slightly more control, but no one in real applications talk about it. But it's really caused some problems in mathematically. Okay, so if you can, so the problem is in this system. So here's U, right? This is U, the control, external control. But for this first part, it's open loop dynamics. So this part is the control. And here is no control. It's natural dynamics. So if you don't control this system, it could be unstable. Okay. For example, like fx is x, right? And this solution, which is a linear system, right? Okay, we assume that fx is x. Then this system will be unstable, right? The solution you can solve for this because it's a linear ODE, and the solution is unstable. It doesn't converge to 0 in time. Okay, so you can add one more, add the controller, right? And here, xt will go to infinity as t go to infinity, right? X increase with time. So to prevent this dilemma, you can, and in this case, after you add another external controllers, your solution might change, might converge to 0 as t go to infinity, right? So this is from the contribution of this control. But this control so this called closed loop dynamics, right? Okay, it's kind of feedback after you add this term. But if you are interested, or you can evaluate the solution of this ODE. Okay, let's say, did anyone know what this function looks like? So sine function. When x equal to 0 is 0. X, and it's minus 1 if x is smaller than 0. So the question is this function, sine function, continuous? Is it continuous? No, right? There's a jump at 0, so it's not continuous. So, which implies even it's continuous, this is not continuous. The summation is not continuous, right? So, it's not continuous. Not continuous. Or C0, right? Not continuous. And as we taught from previous week, here it says if f is continuous in the region, in this R region, where the initial condition located, right? Then you have a solution. But now here, it's not continuous at 0. Right. So if your initial conditions is our objective, okay, but if you start your initial condition is 0, where this is not continuous, then x, the solution doesn't exist. But in reality, in real applications, sign function, because of the dynamics of the mechanical systems, this doesn't exist. You cannot really do a high frequency switching, right? When you are on the neighbor of 0, like if you are on the right hand side, a little bit right of this 0, sign is 1. Otherwise, it's -1. But it's hard to really switch that fast for your mechanical systems. So in real mechanical systems, usually it's continuous. But for mathematical model, it's not continuous, right? Okay. But if that's in real case, if that's true, which is not continuous at here, and if you start from here, I don't know what's going to happen, but the solution doesn't exist. Okay. Is that clear? Uh, 如果你做过马达控制，你就知道，如果你 apply 这种 sliding mode control， 它会一直在平衡点那边切换，它不会停下来，所以你马达也不会 generate any work， 就是不会有做任何功。那它就是，但是你有输入能量，所以它就以热的方式呈现出来，那你马达就烧掉。Okay. So if you apply this kind of control to your motor control, the motor doesn't go anywhere. It just oscillates around 0. But actually you have power input, right? You have voltage, you have current. So the system absorbs the energy, but it doesn't generate any output work. So the net energy will be converted to heat and dissipate to the nature. And eventually the temperature of motor will increase until it's burned out. Okay. So this is not a good controller in reality. Okay. And maybe like after week 10 or 11, 12, we will introduce you another controller, which is kind of integration of sign function. So it's continuous now. Okay. So it's a much smooth control compared to the sliding mode control, and it's called REACHABLE. Control. So now we have bridged the gap between existence, uniqueness, and to this example, right? To this real dynamic system example. So is that clear? Okay. So next, reachable set. So reachable set is the same as controllable set, right? If you can read that definition, basically it means the controllable set. Set means a collection of states, X. So given a linear system, which is a function of x, not only x but also u. So basically it's a closed loop system because you have control. So let u be an open set of dimension m. Okay. And x0 bar is Rn, the reachable set defined as Ru, which is depend on the initial condition and capital T for a given non-zero time. It's defined as a set of all x, capital T, where this x from 0 to t is belong to the Rn set, and the control is belong to Rm set. Okay, so this set is defined as a reachable set for this dynamics. So basically this is reachable set U So assume initially you are here. Okay, you are here, which is x0, right? Initial condition here. Initial condition, you start from x0 bar, and you apply some ut, okay, belong to this set. T, okay. Okay, so this point represent a point in this set. Okay, and next time after you at this state you apply a control, you might reach to the next point, which is xu, right? And you apply another u. Okay. So if you repeat this, you might have this kind of configuration. So each point represent a reachable set. Okay. So the collection of all these points is a reachable set, which means if the system is controllable, this point should cover the space of all your state space. So you can control, given any state, you can use a control to go anywhere in this set, which is reachable. So it's called reachable set. 能懂吗? So it is, I think it's more, is a more mathematical term, but this is my explanation. Any questions? 没有问题。反正就是 control， 就是 set 就是所有的集合嘛。那集合就是由点构成的，那所有的点就是它可以被 control 的那些点。OK， 这个点包含了所有的 state， 所有的 control， 能懂吗 ？Any possible states that is reachable given any control input. Okay, the collection is a reachable set. Okay, so any question? 听得懂吗？Okay, let me give you an example. A car. You can apply so given a car and the state x, okay, it could be x1, x2, could be position or velocities, and here is your acceleration, which is similar to the amount of gas that you put into your agent, or the angle of the pedal, right? So the point here is given a state, the amount of control you put into the system. This combination is a point in this set. Okay. So you can imagine that the next state of after x and u, after giving us current state and you put some control input, the system will reach to the next state, right? X, t, right? And at xt you put another u, which is maybe a, t, okay, and so on, right? A reachable set will be a point here, a point here, a point here. Every possible state the collection of all these states are reachable set. So let me ask you a question. Car cannot fly, right? So if you call some set here, which is z equal not equal to 0, or the height is not equal to 0. This set is not reachable for this dynamics, right? Is that clear? Controllable of the linear systems. So we have mentioned controllability for linear system and nonlinear systems, right? But for any linear systems, you can, for any nonlinear systems, you can linearize the system at any point. So theta is equal to the x1 state, okay? And theta 2, so x1, x equal to x1 and x2, which is c times theta dot. This is theta, okay? And you have in here the pendulum, the length of pendulum will be L, and you have mg here and some t here. Okay. So the dynamics of this system is represented at this ODE. So it's nonlinear, right? Because your state, which is x1, is a sine function. Okay, it's nonlinear. But this system, this nonlinear system, can be converted to a linear system. 线性化. You linearize this. Okay. So the way, the problem is for nonlinear system, which is x1 dot x2 dot L minus I is the inertia. U control input. Okay. We want to convert to a linear system. Okay. We want to convert from nonlinear system to a linear system. Okay. Which means that you need to find a way to decouple these nonlinear functions. And the way is using this approach. So this A, the relation between the A to, so we say in general, XU. Okay. This. How you convert a nonlinear system to a linear system. So the relation between this F and A is A equal to partial X, partial F. B equal to partial U, partial F. Okay. Why? So it's clear that the dynamics is this, right? It can be represented by this. But what does this mean in this picture? It means, and one more important thing is you have to evaluate this because it's a function, right? 你做完 partial 它是个 function. It's a function of x and u, right? because f is a function of x in U. So after you take the partial, you need to evaluate where is the point of interest, right? So if you are interested at x equal to x0, u equal to u0, then the M matrix will be different, right? It's a function of x and u. So given different point of interest, this M matrix will be different. That means if you are interested, if when you linearize a system, you need to choose at which state and given which control input. Okay. And the selection of these two have a constraint, which is x0 and u0 has to be 0. Okay, which means you have to evaluate at the equivalent point. So if you are interested at this configuration, say 30 degree, I want to see at 30 degree what's the linear dynamics of this pendulum. And you can imagine that the dynamics is totally different compared to at 0 degree, right? 对吧? Okay. So the partial of x, f, with respect to x is this function, okay? U is these functions. So in this matrix is a function of x, as I mentioned, right? So you need to substitute what is the point of interest. So next is we substitute x0 and u0 to this. Then you got a constant matrix, right? So now A becomes a constant, B is become a constant, which is the spirit of a linear system, right? 对不对? 懂吗? Remember in the linear system, this had to be a constant, right? And now, so this is the linear system at this state, right? So if you change to x0, maybe 30 degrees, so you put here as pi over 6, then this value will be different, which means your MS will be different. So the linear dynamics is different at here and different at here. Okay, depend on the location, depend on the state. 懂吗? So now, so you can imagine what's the difference, why you need the nonlinear controller. If you use a linear controller, you can only apply to this kind of system, which only guarantees stability around this point, right? Because when you are away from this point, the dynamics totally changed. And the same controller cannot guarantee stability for this system, right? So if you design a nonlinear system, it guarantees that no matter what is x1 and y1, no matter at which state, this controllability, this U guarantee the stability. So, okay, so this property is said, so previous slides, local controllability. If you linearize any nonlinear system, the stability is only controllable, or the stability is only local. Okay, everything is local. The properties are local. Controllability is local. Stability is local. Okay. So here is the math, the background over here. Okay. So here I told you how to linearize a system. So given any nonlinear system, okay, which is this, the linearization of this nonlinear system around some point can be approximated as this. Okay. And the delta x is defined as a perturbation around the equilibrium point, or around x0. U is the perturbation around the U0. Okay. X0 and U0 is here. And your A will be evaluated is the partial of F evaluated by X0, U0, same as U. Okay. And these are the elements you construct the linear system. Okay. So here, this delta you can consider it as a transformation of coordinate. 你偏移，你把你的坐标偏移的。You translate your x coordinate to by some x0 value. You transform your control to some u0 value. So you which is you move all your system to equilibrium point, right? For example, like evaluate what's the linear property at the equilibrium point. Okay. So at 0 at 0, u is 0 at the 30 degree, which is pi over 6. The element in this A matrix is different, okay, which represent the dynamics are different. So what is U0? U0 and X0 have to satisfy this, right? Because at that point, X0 will be stationary, right? If this is satisfied, it means that at that point, this is stationary, okay? So, any questions? Hey.
Please go back on the free page.
Huh?
Please go back on the free page. Oh yes, this one. So from this slide, I understand that if we can linearize the nonlinear model to be the linear model here, and the conclusion of this slide is that then the system is controllable around x0 and x0 and y.
Yeah, so I think I missed something. Hey.
A little bit wide here because we have to check the condition of A and B before we can make this conclusion.
Yeah, so we need to check the matrix B, A, B.
Yes.
Yeah, so is that your question?
Yes, but because this slide I don't say that.
Yeah, so sorry about that. Okay, I will take care of this part after the class. Okay, thank you. Any other question? If there's no question, so another new concept is observability. So before we talk about controllability, here is observability. So what's the difference? So the condition for a linear system to be observable is this matrix have to be full rank, okay? And this matrix consists of C, which is a row vector, and A, which is a n by n matrix, okay? So so before we haven't mentioned about the second part, y is equal to cx, right? Okay. So here is fine, but what is c? What is y? Y is the measurement, okay? measurement. And C is just some coefficient, okay, some row vectors. For example, 0, 0, 1, or maybe 1, 0. No. Okay. So if your x, which implies your x is 2-dimensional, right? Okay. Then your y will be so what this says is y is the measurement, okay, and assume that in the example, the same previous example, right, car x, you apply some u here, x is x1, y x2, okay, or position and velocity, okay, and y is the measurement, right? And it's not full state measurement. It can only measure the first element x1 because of the C matrix. Okay, this says that in this system, only position is measurement. Okay, it is measurable. Okay, only this is measurable. This is not measurable. Okay， 这样是什么？这个情况就是类似于in this case it's like the car. On top of the car, there's a LiDAR system. Okay, there's a LiDAR system that detect maybe here. Okay, there's a building, and it can measure the distance. Okay. So the building is like a like a remark. So implement this kind of rangefinder sensors. It only detect the range, okay, to these buildings. So using some estimator, this information can be used to estimate the location of the car, right? But the velocity of the car might not be measurable, right? 对不对？你只知道它的距离，或者说你只知道它在它的移动多少距离，但是它移动的速度你不知道。但 of course you can use numerical methods to evaluate the velocity, right? Given for example, x1 t plus delta t minus xt, numerical method to get the approximate value of its velocity, but it's not reliable. It's very sensitive to noise. If you have some high frequency noise, when you take the derivative or numerical derivative, this guy will be totally destroyed. Okay, 懂吗 ？OK， 你微分它是对高频的东西非常敏感的。OK， 微分就是有点类似于在那个 Laplace system 你给它一个 S 嘛 ，S 你不就是一般什么 in Laplace system in S is equal to you put S equal to J omega, right? 所以 omega 带进去，这个 omega 不就是 frequency 吗？当你有高频的 frequency 在里面的话，当你有高频的东西在你的 frequency 的话，你把它带进去，这个东西会变很大 ，OK？ 所以这个东西会对高频的东西会非常敏感。 So anyway, it's very sensitive to noise, okay, using this numerical method. So we don't recommend that you use approach to estimate x2 given x1. Okay. So in this system, the measurable term is x1, not x2. So that's why you put 1, 0 here. Okay. So observability means given this measurement, okay. Given this measurement, I know this is measurable, but can this one also be measurable? If both every state in here can be measured, can be estimated by this measurement, then it's observable. Okay, 这样懂吗? So it's very similar to controllability. The only difference is controllability is evaluated from the input here, U, right? We're given the input, we want to see if every element in the state is controllable. Observability is given this measurement, the other way, the reverse way, right? Given Y, if every X is measurable. 能懂吗? So the design of controller is a little bit similar to the observer. Okay, 是非常像的. Okay, that's observability. So I think that should be clear, right? So in the C matrix, you replace B. In the controllability, we evaluate B, A, B, right? Here is C, C, A, right? Okay, you just replace B by C. Because A remains the same, right? A is here and here. Because A is the propagation of states between different times. Okay, A is the natural dynamics. But C depends on which element, the input is from which element. Okay, same as B here. Okay, so here's controllability, and we have mentioned this before. Stability means it always bounded. Okay, unstable means it's not stable. It's not bounded. Okay, so here is these two are complementary. And for asymptotically stable means it's same as stable, but it have to ensure as t go to infinity, the state have to converge to equilibrium point. Okay, usually it's 0, 0. Okay, this doesn't require the x goes to the equilibrium point. Okay, it just had to be bounded by some distance epsilon. Okay. So next time I will give you the definition for positive definite and positive, the positive definite function is looking like this. For example, x squared, x1 squared, or x2 squared. And semi-definite, positive semi-definite is something like this. And negative definite and the above functions. Okay. So that's for today.